Let's begin by creating a new application. Let's create a simple console application in C++. Let's call that Darkside 2 just for fun and put it in this directory and just create the project. So the first thing we want to do is to be able to create a minimal application that has no exports. Maybe that's actually easy to do. Maybe all I need to do here is just start with a blank sort of application, just return 0 here and see what we get. So let's build that and let's open that in Explorer. So here it is opening on my other screen. So I'm going to go ahead and take this executable and drag it into Total PE, which is my PE viewer, but of course you can use any PE viewer that you like. Once we do that, we can look at the imports by double clicking. You can see there are a few imports already there. And you might find this weird because we've just created a new application. We are doing absolutely nothing. So how come we have all these imports already part of our project? And so the reason is that, in fact, although we don't have anything here except a simple main function, the main function is not the first thing that is being called in a process. In fact, the C runtime calls our main function. The C runtime is almost the first thing that is running within the process. So in order to make the application more minimalist, so to speak, we have to ditch the C runtime. Let me use close here to remove the loading of the binary into Total PE, so I'll be able to make changes. And let's see if we can make things better. Let's go to the properties of the project. And I'm going to use all platforms here and all configurations so I can do these things just once if I later decide to compile for x86, for example, or whatever. So let's go ahead first and go to linker and input. You can see there's this option to ignore all default libraries. So let's select that to be yes. With that, we're saying we don't want to use the C runtime and any other default libraries that might be configured. Let's try to build this. When I try to build it, you can see there's an error here. In fact, it's a linker error, 3 errors that's saying that we have some unresolved externals, some functions that the linker is looking for that don't exist. And this is because we removed the dependency on the CRT. So the CRT has provided a few functions. One of them is the startup function called main CRT startup that we need to provide ourselves. So let's go ahead and change this to main CRT startup. It's just a name. In fact, we can even change the name by using another linker setting, but let's just keep that for a moment. Let's build this again. So now the linker is a little happier. There's just these two functions that it's looking for. So they're coming from other stuff that is by default provided to us, but in this case, we don't really want that. So in code generation, we want to remove stuff such as the security check here, and we want to remove anything that provides some kind of checks at runtime, such as these checks for stack stuff. I'm going to just change all of that to default, which actually means absolutely nothing. Let's try this again. And now we can see it's compiled and linked successfully. Let's see what does Total PE have to say about that. Let's go to that file here. And you can see that now we actually have no import directory at all. It just doesn't exist at all. So in fact, we can even work without any kind of import directory. But to mimic what Darkside does, let's add just a single import for exit process. We don't actually have to call it, we just need the code to exist. So I'm going to call exit process here. Even though it's under e false, it's not going to be called really, but we're going to use that to force the linker to add the import section to the binary. I'm going to add an include to windows.h so we have a definition for what exit process looks like. Once we build that and go back to our Total PE, try this again, we can now see that we have an import table here and we have a single import, which is exit process. So you might be wondering, why is Darkside actually creating that single import? So there could be one of two reasons, or maybe two potential reasons. One is to be perhaps less suspicious, because if you have no import directory, you're probably very suspicious. At least there is an input directory for someone that tries to look for something like this. So at least we get something. The second reason might be that just someone was having fun and would love us to ponder this exact issue. Anyway, so now we have something that looks similar to Darkside in the sense that it has a single import dependency on exit process as part of kernel 32. A second possible reason would be, by the way, to force kernel 32 to be loaded into the process. But in fact, even if we didn't use that, kernel 32.dll is always loaded into every user mode process unless you're writing something which is completely native, that doesn't use any kind of APIs except NTDLL. So it's probably not a good reason, but still a reason nonetheless. So now that we have that, we want to start doing something. And what the ransomware wants to do, obviously, is to be, ransomware, to be able to encrypt stuff. And for that, it needs access to certain APIs, such as create file and the load library perhaps, and read file and write file and things like that. So in order to get these APIs, we need to call this function called getProcAddress. And so if I would call getProcAddress, I'll be able to get any function from any loaded DLL in the process. And that's very easy to do. However, if I call getProcAddress directly, then I'm back to square one. GetProcAddress will be part of the import table, and then perhaps antivirus software can say, hey, someone is calling getProcAddress. That's very suspicious. Let's flag this thing as potentially malicious. So you want to call getProcAddress perhaps, but we need to locate getProcAddress manually. Instead of just calling, we need to locate that manually so that it's not going to be part of the import table. So for that, we need to write some function, and that function will be something like finding an export. So let's go ahead and call the function called find export, for example. And for that, we're going to need the name of the DLL. That's going to be kernel32.dll, maybe some other DLLs that we might need later on, but we'll write something which is generic enough, and the name of the function itself. And the name of the function is going to be a simple string, that is an ASCII string, because this is how things are stored within the import table, and in fact, these are functions, how these functions are exported. So we need that, and we're going to return a pointer to where the function is actually in memory. I'm going to cast that to whatever is necessary. And so in order to do that, what do we need to do here? So there are a couple of things here which are non-trivial. The first thing is that we need to actually go and look for the export by examining the PE, the particular PE that this DLL represents. And before we are able to do that, we actually need to find this module loaded into memory. So how are we going to find it? So as it happens, the list of DLLs loaded into a process is stored as part of the process environment block, or PEB. So if we have a pointer to the PEB, then we are on our good way to locate the DLL. So the process environment block is not really fully documented officially, but it has enough documentation in Microsoft provided header called winternal.h. And this winternal.h provides some parts of the process environment block. If I press F12, we can see the definition. You can see lots of stuff here is just provided as reserved, so Microsoft doesn't want to expose that. But of course, we can get the full definition of the PEB using a debugger, because the symbols are available and all that stuff, but we don't actually need this for our purposes here. And so one of the things we need to look at here is this LDR data structure, which is another pointer to another structure, which again is partially provided here by the winternal.h header file. And what we have here that is documented is an in-memory order module list. That's the list of modules in the process stored as a doubly linked list. So if we go over that list, we'll be able to find structures of this kind, LDR data table entry, and this is where we can find the name of the DLL. You can see it right here, the base address of the DLL, which is what we need. So we can go ahead and use this information to find our DLL, and then our second step is going to be to parse the PE itself to locate the exports and find the specific export we're looking for. So obviously lots of stuff to do, so let's begin. The first thing is to implement this idea of locating the DLL within the PEB. So first you might be wondering how we're going to get pointed to the PEB anyway. Although we can write this function, how are we going to call it? So what I would like to do here is to do something like this. I would like to call find export and give it the PEB somehow. And then we're going to use kernel32.dll. This is what we want to look out for. And the function name should be getProcAddress. If I get that, then I'll be able to locate other functions more easily without repeating this find export call, which I could do for any kind of export really, but once I get handled to getProcAddress, I can get the pointer to this function, I can use that to my advantage. So we need this getProcAddress, so let's go ahead and find it. So let's call that pgetProcAddress, and we're going to do some casting here. So since we have the prototype provided by the compiler, we can use the C++ decal type expression to automatically cast to the correct type without us having to actually use a function pointer type here, which is more verbose and error prone. So if everything goes as planned, I'll be able to get the pointer to get proc address, and from that I'll be able to start getting addresses of any other function that I like. And so the only remaining problem in calling this function is the PEB. So as it happens, this main CRT startup, in fact, any startup for a true process actually is provided with the PEB. This is also where the command line arguments are stored, by the way. So normally when we write a normal application, we write a normal main function, the C runtime gets the PEB and parses that to whatever it needs to get from that, such as the command line arguments, and then calls our main function. But now we have no dependency on the C runtime, so we have no dependency on main, and it's up to us to do all the work. So we're actually going to get the PEB here. So I'm going to grab the PEB and pass it here. So now we can move forward to our next step, and the next step is to locate the DLL. And remember, what we have here is a linked list, and that linked list is actually very common in the native API and in the kernel that is built around a structure called list entry. So we need to go to the PEB, and we know that there's the LDR member there, and this is where we find the in-memory module list. This is in fact the header of that list. So I'm going to grab the address of that header, because as it happens, this list is actually circular, which means that the last item points to the head. So when we iterate, we can't look for a null pointer or something, because that will never happen. In fact, we have to iterate until we get to the head, back to the head. So I'm going to have a next here. Next is going to start with head, and let me just do that properly. So head f link, that's the forward link, that's actually a pointer to the first item. We're going to move as long as next is not the same as head, so we're not back to the head, and for every iteration we're going to move to the next item by using next and then f link. That's going to be our loop. This is a very common way to iterate over list entries. So now that we have each one of these entries, we need to actually grab them first. So the entry itself is built around this idea that every structure, and the structure we're looking at here, let me go back to the structure here. The way this works is that list entries are actually very generic. They just point forward and backwards to the next item. They have no type information indicating what they're actually pointing to. So what they are actually pointing to is, in fact, if we go back here, they point to this data structure that looks like this, as I mentioned already, but specifically the actual list entry points inside here. So in fact, we need to go back in memory a little bit to get to the beginning of this structure for this to work correctly. So fortunately for this kind of case, there's a macro provided by Windows, by the Windows headers, called containing record that moves the pointer back the correct number of bytes. We can do that ourselves with just a simple, relatively simple macro. So we have our address, which is next, and then the data structure we expect that to be is LDR data table entry, and the field itself has this name called, as you can see here, the name is in memory order links. That's the one that points to the next and the previous item. So we need to provide the member name. And this gives us the actual entry, which is already being cast to this kind of type. So this containing record macro is nice enough to cast this to this data structure. So now that we have that, we can look at this entry. And as part of this entry, there's the full DLL name. But of course, we need to compare that to the DLL name we're looking for. And in this case, we have two issues. One of them is the fact that this is a full DLL name, so it contains the full path, including drive and directory, which we don't really care about. It's usually C, Windows, System 32 and so on, but maybe the machine has installed Windows on say D, on the GD drive. It is possible to do. So we don't really want to deal with that. We just want to look for the last piece of the name, which is just the file name. The second difficulty here is that the structure being used to store this string is called Unicode string, which is a string descriptor, and this is a very common type used by the native API and the kernel itself to represent strings. And so we need to deal with that. And Unicode strings generally have two members of interest. One of them is the pointer to the actual characters, and then there's a length in bytes of the string. This is of course a Unicode string that is 2 bytes per character. So we need to do some searching here, and the string might not be null terminated, by the way. Unicode strings don't have to be null terminated. So again, it makes searching a bit more difficult because the normal functions that do searching, like WCS-CMP and stuff like that, they look for a null terminator. In any case, we can't really call these functions directly because we have no dependency on the C runtime, and we don't want to add that dependency. So we're going to do this in the old-fashioned way, so to speak. We're going to do this manually. So I'm going to grab the last character and going to search backwards until we get to a backslash, and then compare that to compare these characters to the actual DLL name we're looking for. So we'll take the full DLL name. Let's take the buffer. That's the pointer to the beginning of the string, and then let's go ahead and take the length of that. So full DLL name dot length, and the length happens to be in bytes and not in characters, which is a bit perhaps confusing. So we need to divide that by 2. So I'm going to get that's going to be the last, or actually one after the last character, and then we're going to go ahead and try to make the comparison in some way. And so the second thing we need to know is the length of our original string we need to look for, that is the DLL name. What is the length of that? Normally we would call the WCSLen function to get that length, but unfortunately we can't do that because that would necessitate calling the C runtime function, which is exactly what we want not to do. So one option to get around that is to write our own variation of WCSLen. This is not a very difficult function to write, so we can do that ourselves. Just write some kind of private function called WCSLen2. I'm going to call it 2 just to make it clear that we're not actually we're not calling the C runtime function here, but using our own implementation. So we can do something like this. Length is going to be 0, and while we don't have a null terminator, we're just going to increment len here and return len. So that's not a very difficult function to write, and if you feel a bit rusty, you can find such implementations online. So now that we have the length of the string, we're going to compare characters from the last to the first. So I'm going to have a while loop here where I want to grab the last character, but first I'm going to move back, so I don't want to, because we started with one past the string, I'm going to go back and then look at at the character here. We need to make sure that this is the same as DLL name at index I. Exactly the same idea. I'm going to move back in memory. And while this is the case, I'm going to do nothing and move forward. And once we're done, we can look at the character there in either string. If it is in fact a backslash in last, it means that in fact the strings are the string is the one that I'm looking for. If it's not a backslash, then it's not the same string because there's some other characters which are not the same. So if this is the case, we can do something. So we found this particular DLL, and we can move to the next stage, which is parsing the PE of that DLL. Otherwise, we're going to continue searching with the next entry. So this is almost right. The thing is that this comparison compares characters, but it doesn't take into consideration the fact that this might be case sensitive. And so we need to provide the correct case to this function, which is tricky. Maybe the file name has different case on different machines for whatever reason. So I need to make this a case insensitive search. And the way to do that is to remove the fifth bit. So I'm going to remove the fifth bit, which is going to treat these characters as uppercase. So it's just going to make them uppercase if they're not uppercase already, just to make it easier to search without us having to be exactly right in terms of case. So just as a simple example, if you look at capital A is 41 hex, small a is 61 hex. So there's a difference of 20 hex. This is just bit 5. So I'm going to remove this bit by ending it with a not. So I'm going to just zero out that particular bit. If you're not familiar with how these things are working, these and the not stuff, then you should definitely visit our workshop. Anyway, once we have that in place, we have found our DLL. If we go all the way to the end, then we haven't found the DLL, so there's nothing we can do except return null, indicating there's nothing to do here. Otherwise, we have our base address. So our base address, let's go ahead and in fact, I'm going to return the base address to whoever is interested. So let's go ahead and have a base address here. I'm going to return that to the caller because the caller might need that later on, especially when calling getProc address. So let's just fill in the base address here with what we have found. That's going to be our entry, and that entry now has this particular member called DLL base. That's really what we want. So I'm going to grab that, and we're going to now call a helper function called getFunctionAddress, where we're going to provide the base address and the actual function name we're looking for. This is the part where we need to parse the PE. Going back to this location here, we do need the address here. So let's go ahead and get this base address. Let's call that base address as well, and just get it here like so. I'm going to use a reference here to just write this to the caller's provided address. So once we have that, we have the first stage complete. The next stage is to implement this function, getFunctionAddress. So let's go ahead and do that. So the function address is going to get DLL base. So we have a base address. Let's call that simply base. And we have, of course, the function name. So now comes the second part, which is even trickier perhaps, which is parsing the PE. Parsing PEs is not perhaps very fun to do, but is sometimes necessary, especially in these kinds of cases. And we're going to have to do some of that work to get to the exports. So let's begin. First thing we need is to start with the base address. What we have there is an image DOS header structure that represents the beginning of this file. So I'm going to take this and simply cast this base to some helper pointer P to make it slightly easier to work with. And this data structure, as you can see, it seems to be understood by the Visual Studio environment. That's because this is defined within winnt.h, which is one of the fundamental header files that the Windows headers provide. So in fact, most of the stuff that you need for parsing PEs in terms of structures do exist already as headers. It's just a matter of doing the right thing. So this DOS header has been around for many years. What we really want is to move forward to the NT header. And again, we're not going to discuss the PE format here, but in the full course, we're going to discuss the PE format in much greater detail. So it happens to be something called NT headers, image NT headers. I'm using a 64-bit application here, so I'm going to grab a 64-bit variant of that. And it happens to be in a pointer, which is at some offset provided by this image DOS header, which is called elf new, something like this. So this is just the offset to where the actual interesting header begins. So I need to add that to the base address. And the base address can be P or base, doesn't really matter, it's the same value. We just need to cast that to a pointer to a byte to make sure that this addition adds bytes, because by default it actually adds whatever the thing we're pointing to. So we're pointing to image DOS header, it would just add image DOS header times the number of the number that is here. So we want to make sure that we're doing the right thing. Remember, when doing pointer arithmetic, the addition adds not in terms of bytes necessarily, but in terms of number of items times the size of the item you're pointing to. So I want to make sure the compiler understands we're pointing to a single byte here, so this would actually add a number of bytes, and this kind of idea repeats itself. So that's the main header, and that header contains something called an optional header, which is in fact not really optional. What we really need to do is to grab the export directory, which is part of the PE. So here's how to do that. We need to go to NT header, we have the optional header, and then we have a bunch of data directories. And there are 16 at most data directories. What we want is the index that represents the export directory, which happens to be 0 by the way, but it's the first one. But we're just going to use the constant, which is again defined in winnt.h. So we have the export directory here, and every directory entry there has an address and a size. And so we need to get to that particular location and then cast that to what we have there as the export directory. So I'm going to use the cast to export directory. That's again a structure provided by winnt.h. We just need to get to it properly. Again, I'm going to cast to byte here and add to it what we have in xdir, which is the virtual address here. So the virtual address is not really a virtual address, it's a very misleading term. It's actually called the relative virtual address, or RVA, which is basically the offset from the beginning of the file in this kind of case. So I'm just going to add that to the beginning of the file to get to the actual address in memory, because remember, this DLL is currently loaded into memory to get to that export. And we can also look at how many exports we have. We just need to now go ahead and search for these particular export. So in fact, we can search the way getproc address actually works behind the scenes. When you call getproc address itself, it actually uses a binary search. So it takes advantage of the fact that all the exports must be sorted, and they are sorted. And so we can search for it pretty quickly by using this idea of logarithmic search or binary search when we have logarithmic time. But I'm going to use a simpler approach just to search linearly, just to make it easier to understand. It doesn't matter that much, it's not going to be that much slower. I'm going to do that just once, and after that we're going to call getproc address as many times as we need. And even if we use the linear search for a bunch of functions, it's still not really that critical for this kind of application for sure. And so there's some complexities here which happens to be related to the way the names are provided here. So the actual names of the functions are provided using some kind of offset. So again, we have to grab this offset from the exports, and here we have the address of names where the names actually start. But again, it's not really the address, it's just the offset there. So we need to grab the address of that and then the reference to get the actual offset. And then the actual names are going to be related to that exact offset. So going to be a character pointer here, and we have again p byte, but this time to add the names offset. So there's some indirection here. It might look a bit complex at this point, but once you dig through the data structures that make up a PE, it would start to make sense. But this is fairly, I would say, standard in the sense that you can find this in many locations, many sources, that you have various ways to read information from PEs. And that's the names. Now, the second thing that we need is the actual beginning of addresses. Where are all the addresses? And we're going to just keep a pointer here to this set of addresses. So we're going to use them based on the index once we find the actual name. So there's address of functions where the actual addresses are. So what we need to do here is start to do some search. So we have a loop here running from 0 to count. That's the number of exports that we have. Now we need to compare the strings here. And the way this works is that the strings are null terminated. These functions just follow one another in memory. And since I'm not going to use the binary search approach, I'm going to do the searching manually. So we need to compare two strings. First, we need to compare the string here that we have, which is names, the one that's going to then move forward to the next string, and the actual function name we need to locate. If this is in fact the same one, then finally we have the result. We just need to return the address of that function based on that index. And again, we're going to add the base address here. So that's all we need to do in that respect, but unfortunately it's not that easy. There are a few complications here. The first one is the fact that strcmp, again, this is a C runtime function which we can't use. So we have to, in this case, implement our own strcompare function, which we can. Again, not super difficult, but let's go ahead and do that. So in fact, I'm going to do something slightly different. I'm going to create a Boolean related function called equal strings. I'm going to have one string and another string. Just compare them and return true if they're the same and false otherwise, instead of using exactly what strcmp does, which also returns if one is greater or smaller than the other. And so let's do something here. Let's go ahead and make sure that while s1 is not null, so while we are not reaching the null terminator in either string, and we have the fact that the both of these characters that are being pointed to are the same, then we can move to the next character. And then once we're out of this loop, the strings are equal if both of the pointers point to null terminators. If this is the case, then the strings are equal, otherwise they're not. This is just one way of implementing that. It might not be the most efficient way, but it is efficient enough for our purposes. So I'm going to go back to this code here and change strcmp to equal strings. I'm not going to do equal 0. In fact, I'm going to treat that as a Boolean and just use that. So if it's not that correct string, we need to move to the next string. So I'm going to use strlen2 here, which is our, well, actually strlen we haven't implemented just yet. We need the length of the function, and then skip the null terminator. So again, strlen, we can't call that. We need to create our own strlen function. I think did we do that already? strlen2. Oh, yes, we have a variant for a Unicode string, but now we need to have a variant for an ASCII string as well. So I'm not going to use any templates here, just going to do some copy pasting here very simply to change the string type. Okay, going back here, we have strlen, moving to the next one. Is that all we need to do? Well, almost. So first, of course, if we get to the end of the loop, we didn't find the function and there's nothing to return. But there's slightly another complication here. It has to do with the fact that some of these functions are actually forwarders. Let's see an example of that. Let me open here something like kernel 32, which we're actually want to use. So let me see if I have that somewhere here, which I really should. Okay, apparently not here. Let's just open it. So here's kernel 32. These are the exports we're looking for. And one of them, of course, is getproc address. This is the one we want to locate. So you can see here the function RVA and the name RVA. So that's a big help when you're trying to debug this kind of code to make sure you're parsing the PE correctly, and ordinal is really the index of that function. So this is very helpful. But if you look at some of these cases, some of these functions are actually not functions, they're actually forwarders. They're forwarding the implementation to a different DLL. So it's not really implemented in kernel 32, but in fact implemented in a different DLL. Here is an example for kernel base. Here's an example for anti-DLL. These are different DLLs. And so these forwarders don't really point to real functions that have real code in this DLL, but actually pointing to another. And so we need to make sure that we don't accidentally land on a forwarder. We have to actually skip these forwarders. And the way to tell whether we're in a kind of forwarder or a real application is by looking at the address. The address that is pointed to by this index. If the address is somewhere within the export directory, in terms of its address and size, then this is a forwarder. It's not a real function, it's just going to forward to a different location there where the full name of the forwarder function is. So we need to make sure that if we do encounter this kind of case, we have to skip it properly. So if the address that we have is within the export directory, then that means this is a forwarder. So we're not going to just use the size here to verify that. And if this is the case, we actually have to skip. And the way to skip is just to move to the next name. Otherwise, we'll find that the indices get messed up and we won't be able to find the function correctly. And that should be good enough. Let's see if that compiles. Okay, so we have here, of course, we have to use plus equals here, and the same goes here. We need to move forward some so-and-so bytes. Okay, so it compiles. Let's now check this, see if it actually works as expected. I'm going to put a breakpoint here by pressing F9 and press F5 to debug this, to run and debug. And remember, we're doing normal software engineering, so we have to debug our code. It's not going to work out necessarily just by guessing. So if you just do F10 here, you can see we get some result, and you can see that the debugger is able to locate the actual symbol, and it is get proc address as we expect. So it actually works in this case correctly. But in fact, it might take you several tries to actually find this to work. And notice that in the list of modules, kernel 32 is indeed loaded, and the address it's loaded in is actually provided here as well. That's the address. So when we looked at the address within the code, we should see the same result. So let's go back here for a moment and go to find export. So notice here we have this check. Let's go ahead and place a breakpoint here. So you can see that the base address is in fact the same number that we see at the bottom when looking at the list of modules. So it has to be the same, of course. It can't be anything else. That's the address here, ends with 64 and all zeros. Notice ends with 64 and all zeros, exactly the same thing. So in fact, we found the DLL, the name is kernel 32, and what we had there with full DLL name is also C Windows System 32 kernel 32.dll. So the case sensitivity here was really important to get around because we didn't provide the kernel 32 name here in the correct case as the way this is installed on the system. So we have that, and then we had to move forward to look for the list of functions. So just to show you what that looks like, here's names. So names is where all the functions are stored. Let's look at some memory here. So here's names, well, almost. So notice the strings are pretty visible here. You can see all these strings, which are the function names, all separated by a null terminator. So they're all null terminated. The second one here is in fact a forwarder, as you can see here. And so on. So this is really where the names are. And of course, we can look at the addresses as well if we so desire. You can see here, well, not really here. There's some stuff here that is being auto-completed without any good reason. So I actually didn't calculate address just yet. So here's a DDR now, really. And you can see here, well, it's actually not very easy to understand what we have here, but these are actually the name, the addresses, the RVAs for this function. So this function. So for example, the first one is 9D 90A1. Going back to kernel 32 here, let's go to the first one. You can see the function RVA is 90A1. So that's exactly what we found, which is the right thing. Just gives a sense that we are in the right place and parsing this stuff correctly. Okay, so once we have that in place, we have the most difficult part here to find get proc address. From this point on, we can look for other functions in a much easier way by simply using this function address. So for example, if I want to find something like create file, so I can say something like create file. Let's create a function here, a variable which I'm going to create as a global variable to make it easier to use in other functions. So you can do the same idea. I'm going to have the create file W function, the Unicode version. We're going to use that one. But of course we could use the other one if it makes more sense. And we're going to, in this case, call get proc address. We need to have the H module. The H module is the base address, in fact, of the module, which we got back here. So it's really where we want to use that. So just to make it easier, I'm going to call that hkernel32 and just cast it so the compiler is happy to an H module. H module is just a pointer to void. It doesn't really represent a true handle. It's just a type being used by the Windows API. So get proc address with hkernel32 and the function name is create file W. And I'm going to again grab this and create that as a global variable so we have an easier time using this information later on in any function that we might need. So here's create file W, and here's how I would define this variable. Again, taking advantage of decal type that knows what this function looks like and can create a pointer to that function. So let's try this again. Let me remove this breakpoint and just press F5. So we land here, we have get proc address available, we have the handle to the kernel module, kernel32, which of course is the same as the base address. And now we're going to grab create file. And if you look at the pointer, you can see that indeed the compiler is identifying the function as, the Visual Studio debugger identifies the function as create file W because it correlates that with symbols and sees that in fact it is the correct function. If the function wasn't correct, I would have seen something completely different. So for example, if I change that thing, say to create process W, which means I would like to find this function, which is also defined kernel32, I will actually find it and the casting would work, but it would of course fail at runtime if I try to call that. So if I look at p create file, it's actually create process W rather than create file really. So obviously I don't want to mess things up in this way. But using this idea, we can then grab as many functions as we want. And of course we can use find something like load library and also use that to load other DLLs if we need them. In this case, we're not going to need any other DLL, but we could have in a different code that we might want to write. Let me just go ahead and grab some of these functions that we might need later on, like maybe virtual alloc is something we're going to need as well. And of course, we have to fix all that stuff to use the correct prototypes, and then we'll have to also create variables for that. So we have write file here and we have virtual alloc that we're going to need, and like I said, we have to go ahead and use the same ideas here to create more of these global variables. So we have read file. It's not very interesting perhaps to watch, but it is necessary. Write file and virtual alloc. Might need some more functions later on, but we can start with this list. So we have write file here. So that's part of the puzzle here. We have these functions that we can now work with. So as an example, I mean, what are we actually trying to do here? We're trying to encrypt files. We're building ransomware here. So to build ransomware, we need to encrypt some files. Let's go ahead and do that and create a simple function called encrypt file that's going to, well, let's call it enc file because there's a macro that is going to mess up the compilation here. So enc file, let's go ahead and create this file name. And what we want to do is to encrypt this file by using simple XOR encryption, but just want to do that for demonstration purposes. So our first order of business is to create, to open a handle to this file. So I'm going to use pCreateFile, of course, as our function pointer. We have the file name, and we're going to use generic read and generic write because we need to read and also write back with the changes being encrypted. We don't want any sharing of this file, no need for any security attributes because the file has to exist. So we're going to use open existing here. And the flags we don't care about, and then template file don't care about either. If this H file is going to return an error, and that's going to be indicated by invalid handle value. And if this is the case, I'm going to return false to indicate a failure. Once that succeeds, we want to read the contents of the file and then write it with some encrypted data. So reading a content of the, so of course not the only way to do that, we can also use file mapping for this purpose, but I'm not going to do that. I'm going to keep it as simple as I possibly can. So we need to also get the size of the file. So the size of the file is supposed to be provided by a function called getFileSize. But again, we don't want to use this function directly because that would end up in the import table. So we want to get something like this. So I'm going to have the H file here, and there's a second parameter which we don't really need, and I'm going to use the code like so. That's going to be the size of the file, so we know how many bytes we need to allocate. So let's go ahead and get file size here. We not just need this function now. So I'm going to add functions here as many as I need, and as it happens, it's all coming from the same DLL, kernel32.dll. So get file size here, let's go back and make it a global variable. So we have get file size pointer, and here's the variable name, like so. Okay, going back here, we have the size. Now let's go ahead and allocate. So maybe you can do another error handling, but that's really not very important for our purposes here. So if, for example, we have a 0 size, probably don't want to do anything, but I'm going to skip all these little error handling just for the interest of time. So now we need to allocate the buffer. I'm going to use pvirtualalloc here to allocate the buffer. I don't care which address it's actually going to fall into. We have the size, and then we need to commit that memory and reserve it as well. So it's just both of them, just normal allocation of memory. And I'm going to use a read-write protection here because I need to read stuff there and then write it back. Again, this could in theory fail if the file is really big or free out of memory, all that stuff. I'm going to disregard that for this demonstration. And then I'm going to call read file to read the data from the file. So we have H file here, number of bytes to read is the size of the file. How many bytes were actually being read? Let's just get that as a result. We have to get that as a result here. So of course we need to have the buffer first. So here's the buffer size, and the final parameter is something which we don't care about. So we're going to get back number of bytes actually read, which should be of course the same number of bytes that are part of the file. So once we read that, we need to perform XOR encryption on the data. So first we need to create some kind of key for XOR. So I'm going to just select some random bytes actually. I don't really care for this example, so we can just do something. It doesn't really matter. Of course, if you want to do a different kind of encryption, you can. Of course, you can increase the key size and all that. That's all good and well, but for our purposes, that's going to be good enough. So we have here the bytes we want to go over. So we're going to go from 0 to size, and for every byte in the buffer, of course the buffer needs to be pointed to a byte to make it easier to work with. Let's just cast that to point it to a byte. We're going to grab here, and we need to perform XOR operation with the key at index I, but we need to have a modulo of the size of this key. so that it warps around once it gets to the end. And that's basically it. Now, of course, the final piece of the puzzle is to write the data back to the file, so it's actually encrypted. So I'm going to use write file here to write the buffer back, and we can now close the handle to make sure that the file is properly closed and the changes have been flushed to disk. So we need another function here, close handle. Okay, fine, let's get it. As you can see, we're adding functions as we need. It's not very perhaps convenient, but it is pretty easy to do once we have the infrastructure in place. So here's close handle. Again, we need a global variable here to make it accessible in any function for simplicity. And that will also end up as part of the data and the data section, of course. Close handle, which you can see in Total PE or other viewers, including IDA if you so prefer. And finally, we're going to return true, indicating that it has been successfully encrypted. Just to test it, let's go ahead and encrypt the file. And that file is going to be, I have a file here, which I'm going to show you momentarily as just as a simple example. An image. So if we call this twice, we expect this to encrypt, and then the second time it's going to decrypt it back, because this is how XOR encryption works. So first, let's compile, make sure everything is compiled successfully. Let's also go ahead and open a command window here to make it a bit easier to work with. So here's my command window. Let's go to x84 debug. So now let's find our nice file. So here's the file. You can see it looks like a Mandelbrot set. For those that are familiar with Mandelbrot, doesn't really matter for our purposes, just an image. And it opens just fine, this mandel.png. So now let's go ahead and run our application. So we have Darkside, let's just run it. It says nothing, but what should happen is that the file should now be encrypted. So let me try to open it again. And apparently it's not really doing its thing, which is of course not good. So something is wrong perhaps. Let's go ahead and just figure out what's going on. We can debug. So let's go into this function. Are we able to open the function? And apparently we can. We have the proper variable here. Let's just go and see the values here more clearly. Let's see the file size. It should be around 60 kilobytes. That's fine. And then we're reading the data here in the size based on size. So we have something in buffer. And if we look at buffer, we can go ahead and look at buffer. We can see there's a PNG signature here, PNG something. So obviously this is the correct thing. And now we're doing the actual changes. So let's go ahead and do Control F10 here. Location, but actually it stopped contagious. Let me just put a regular breakpoint here. There's a shortcut which is not good. So you can see here that we have the data changed because of the encryption. We just need to write it back to the file. So let's do that, and this should write the data back to the file. And just to make sure we didn't mess anything up, I'm going to use the watch window here to verify that. Let's see that we have the correct error. So fine, it looks fine. I'm going to close the handle here, and that's it. So it should have worked. Let's go back to temp here, try to run this again. Yes, I know what the problem is. We actually can't just write it, it just increased the size of the file. That was a bad idea. And so we need to reset the file pointer or just open it from scratch. Let's go ahead and do that in 2 steps just to make sure we do it right. So first thing is to read the file, then we're going to close the handle here. I could just move the pointer back to the beginning, but that would require me to open to add another export for set file pointer. So I'm going to do this the different way. So I'm going to have another crack here by opening the file again, this time for write only. So I've actually increased the size of the file without any good reason. Anyway, that should be still good enough. And then we close the file again. Okay, let's try it again. Of course, we can't have auto again. Let's just remove that. Okay, so let's try this again. So now going back to try to open that up, you can see it's now garbage. The paint can't really open this file. Let's try this again. This should bring the file back, and it does bring the file back. So it seems to be fine, and this is what we wanted to achieve. Okay, the next step that we want to kind of mimic Darkside as much as we can. So we know how to encrypt a file, but you might have noticed that encrypting a file in the real Darkside is happening using that text1 section. So it's a different section. So can we put our function in a different section? The answer is yes. We can use a pragma in Visual Studio called codeseg. We're going to give it a name, text1, just to mimic what Darkside is doing, and then any function implementation between this codeseg and the end of the codeseg is going to end up in that particular section. To verify, let's go back to total PE after we did this change. Let's look at what we have here. Now you can see there's text1 here and there's text. So text has the rest of the code, which is the default section being used for code, and text1 is where our function is. And to verify that further, we can launch IDA. So let's go ahead and launch IDA. I have this IDA here. So I'm going to just go ahead and open that up here on my other screen. I'm going to bring that momentarily so you'll be able to see that. Okay, so let me just drag it here. Here's some IDA view here. And you can see various functions that we have created. The fact that we see the names of functions correctly is because we have symbol files. I've just compiled that. We have PDB files, and so IDA is able to see that. And of course, in real life, once we can remove debug information and there will be no PDB file and you won't be able to see actual nice names, but for our demonstration purposes, it's actually convenient. And so we can see the function enc file here. So it does exist, and there's something here, some code. And in fact, IDA is able here to generate its pseudo or C-like code to show what we're doing in this function called enc file. And again, the full prototype, everything is available because of symbols. But you can see here the calls to get to create pcreate file and pget file size. All that stuff is here, and that's all good and well, like we've seen. And so it's possible to see the code. What Darkside is doing is actually encrypting this text1 section completely, and so that enc file shouldn't really be visible. We should be able to hide it completely because it's going to be in fact encoded using some kind of XOR encoding. So the code is going to be a jumbled mess, and we should find that IDA is not able to actually see that. So that's going to be our next step. So I'm not going to save anything, just close that, and we'll reopen that later on. So the code here is obviously somewhere, but we want to hide it by decrypting it or encrypting it. So how are we going to do that? For this purpose, we're going to create another application to do that offline, because we need to grab the text1 section from the binary and encrypt it and write it back. So we can't do that at runtime. That's too late. We have to do that beforehand using some external tool. Let's create a new project in this solution for simplicity. Let's create another C++ application called encrypting sections. Actually, you can encrypt and decrypt if you call that the same. Again, with the same XOR pattern, it's going to be doing that. So in this case, just a normal application, something going to run offline, not going to try to hide anything here. It's not really the point. The point is to create something that we can work with to encrypt some kind of section in a file. So how are we going to do that? So first we need to get some information such as the file name and the section we need to work with, to encrypt. So I'm going to use the normal argc and argv that we typically use in normal applications. So here's what we have here. And if we have not enough parameters, we're going to have to provide some usage hints to the caller. So what I want to do here is to be able to call encrypted section to provide the image path, that is the file name. We just write file name here. And the second thing is to have the section name. So this is what I'm going to do. I'm going to use a fixed XOR key for this simple example. It doesn't really matter, but of course we can accept that as another parameter if we so desire. Let's add SDIO here for printf management. And so our next stage is to open the file and then as a PE, of course, and then find the section and encrypt it. So let's go ahead and do that. So the first thing we need to do is to open the file. So I'm going to use the create file function here. I'm going to use create file A because I'm accepting these files as ASCII, so I'm just going to work with that. We're going to have to be able to read and write to the file because we're going to read the section name, and we need to find the section, of course, read the section data, and then write back to be as encrypted section. So we have no sharing that we need to do, null pointer, and open existing as disposition. As always, there's no flags that we need here and something like this. If that doesn't work for some reason, we have some bad file for whatever reason, I'm just going to return one here. I'm not going to bother with error handling, just in the interest of time. So once we have that, we need to read the data of these files. So how can we do that? One way, of course, is to do what we did previously. Just read it into a buffer, make the changes and write it back. But I want to do something a bit more, in this case, more efficient. I'm going to map this into memory and then just go ahead and use memory directly and have the infrastructure memory files take care of all that stuff behind the scenes. So I'm going to have H file here. What I want to have here is a mapping. There's no need for security here, and the protection is going to be read-write because I want to be able to read and write to that memory. I'm going to use zeros here to indicate I want to map the entire file, which is really what we need here. In fact, we could perhaps do a bit less than that, but it's just simpler to map the entire file. If that fails for whatever reason, it returns null. Again, it shouldn't really fail unless the system is really out of memory or something. And now that we have that, we can go ahead and close the handle to the file. We don't need it anymore. It's going to be kept open by the memory file object behind the scenes. Next, we're going to map a pointer to this memory. So I'm going to use image.header to start my parsing while I'm at it, and use the function map view of file to map the memory mapped file into memory. So I want to be able to read and write. So I'm going to use file map read and file map write. It has to, of course, correspond properly to the generic read and write we use for the file. And I'm going to start with the initial offset and map everything. I'm not going to do any kind of fancy stuff here to be more precise than that. Again, just for the interest of simplicity, which is good enough for our purposes. So next, we're going to now need to locate this section. So that's another kind of PE parsing we need to do. Okay, so let's go ahead and do that. So first, we're going to need the NT header. And just like before, we can go ahead and grab it, image NT header 64, by going to P and adding the elf new something, which is where the real header starts. Then we need to grab the sections. So the sections follow the headers immediately. So we can use image section header, which is going to be the descriptor of the section, and it's going to be at NT header +1, so exactly beyond the headers. Again, this is 1, but it's not 1 byte. It's 1 times the size of NT header, what that is pointing to. It's pointing to this monstrosity, so it's going to just add this number of bytes, the size of this thing, to the NT header, and we get to this set of sections. The actual number of sections also provided as part of the header. So we now need to run over all the sections that we have. How many sections do we have in the PE? This is provided by the header. So under the header, there's a file header structure there, and there's a number of sections. So we need to find the section, unfortunately, manually by name. So we have that. And now we need to perform a comparison of the section name that we're looking for. And so we have here sections, the name member is the section name. Just need to cast that to a character pointer for the compiler to be happy, because it is set up as an array of bytes, which is almost the same thing. And of course, the name is the one that's provided to us by the command line. So if this is the same, then we have our section. So this is almost right, because if the section name happens to be exactly 8 characters, this thing actually might not be null terminated later on, but I'm going to skip this little detail again for the interest of time. It's not very difficult to deal with that anyway. Once we have that, we found the section, then we can go ahead and perform the actual work, which is encryption and decryption of this section. And so I need to provide the section header here, so we know to find this, and of course the base address, so we can have a chance of finding where the section actually is mapped into memory when we load this module. And then we're done. So we're going to unmap view of file here, and then we're going to close handle for the hmemory file, and we're done. We can just go ahead and return out of this loop here. Otherwise, we can just write some error like saying section not found. So if we manage to go all the way to the end when searching for sections, then it means we have a section that wasn't really properly found. So now we need to have this encrypted section function implemented. So let's go ahead and do that. And really it's just very similar to what we've done in the Darkside actual binary. We just need to perform this kind of operation, but we need to locate, the problem here is really to locate the actual data before actually doing the encryption. I'm going to use the same key just for simplicity. In fact, I'm going to copy this code as well. So let's start with the fact that we have some base address for the binary that is being mapped into memory, and we have the image section header, which is the section we need to locate and use. So in terms of doing the work, we do something like this, as we'll see momentarily. But before we do that, we have to locate where the section data is in memory. And here's where that is going to be. So our buffer is going to be actually section pointer to raw data, plus of course the beginning of the image in memory. So pointer to raw data is not really a pointer, it's again, it's a kind of RVA. So we have to add that to the base address here. And then our size is going to be size of raw data, again provided as part of the section header. So now we can go ahead and work with the same code that we see here, and in fact we're done. There's nothing need to do here further, because it's writing in memory, and of course it is going to update the actual file because we're using a memory mapped file here as our infrastructure. And that is basically it. So let's see if this compiles. Okay, now let's try it. So how do I know that I can try it and it should work? So at this point, we have, well, we've seen that in fact IDA is able to interpret our function in the Darkside clone. But now let's see if it can do that if we change it. So I'm going to use Darkside here. That's going to be our binary we want to change. And the text section that the section we're interested in is text1.text1. So I'm going to do that, and it says section and not found, which is kind of weird. Let's see why a section is not found. It seems to be fine, I think. Okay, if it's not finding the section, then maybe we have something wrong here. So let's just go back to Darkside, make sure we have text1 here, section, seems to be fine. Okay. So let's, of course, close that, otherwise it won't be able to write the changes to the file. Let's see where we are missing something. So Darkside 2 and .text1. I think it looks fine. Okay, since we have no choice here, we're going to do some debugging here. Sometimes we have to do that. This is just part of life. So I'm going to go to x64 and debug. and add these parameters here. In this case, I might need to have the full path here, which in this case is probably going to be necessary. Let's see where things go off the deep end. Let's go ahead and run this. Okay, not good. Actually ran the incorrect project. Let's right click and set a startup project and run this now. So let's see, we have a number of sections here, which is 10 sections, and let's look for the names. So the first name is text BSS. That's not what we have here. argv2, if we look at that, just make sure that everything is correct, is .text1. Okay, good, so that's not the one. Let's continue with the next one. The next one is, right. So I've not incremented the sections there, so that's kind of silly. So I need to increment the section pointer, of course, to the next header. So that was the problem. Let's go back and run this again. So it's run to some kind of successful completion, probably, even though I didn't add any special items there to indicate that. Let's go ahead and load the file again, Darkside, because it has changed. It's supposed to have been changed. So again, it opens to my other screen for some reason. So notice the enc file function. If I try to press tab, you can see that the compilation has failed. So we have junk information there, junk bytes. So the decompiler in IDA is unable to sort out what the code is. It can show us the actual bytes, and also tries to show us something, but this is just junk bytes, If I go here back to my file, look at text1, text1 is now garbage data. It wasn't really like that when we started, when the code was right. So if I go ahead and change it back, we can change it back just by running the same kind of command. Now it's back. So if I go back here, we'll see that the code is now looks very different. In fact, if we close IDA here, and just to make sure that it's not looking at any stale data, I'm going to go back here to open the file again. Again, for some reason, it jumps to my other screen. You can see that enc file now looks good, and if I try to decompile, it decompiles just fine. And so what we need to do here, the last piece of the puzzle, is for Darkside to do these things exactly. So Darkside needs to, before calling this enc file function, needs to do the opposite of encryption by decrypting back the text1 section. So it has to do that itself, otherwise it won't be able to do the work. And so for this purpose, we have to write yet another function. And that function is going to decode the code. So we're going to have a function here called decode code. It's not a very good name perhaps. And now what we need to do is to find the text1 section in our binary right now and decode it using the same kind of, the same XOR key, of course. So again, we need to do something which is very similar to what we've seen previously. We need to find the correct section and all that stuff, and of course using our own function. So let's go ahead and see if we can do that. So we have this. Let's go ahead and copy this here to decode code. So first we need to start with our module handle here, which we can get using, well, maybe we'll just get this as a pointer here to make it easier on ourselves. Let's call that image DOS header here. Let's grab it as that kind of pointer. And now when we're looking for the strings, of course, we're not going to call strcmp, we're going to call equal strings. The function that we created for this exact purpose. And of course, not going to be argv2, we're going to look specifically for text1. Once we find it, then we can do the work to really just decrypt things in memory. Of course, we don't have all that stuff here and no need to return anything here. We just need to do the work to encode or decode back from memory. So let's go ahead and do that. I'm just going to grab this code here. I'm going to use the same key, of course, in this case, just to make sure that everything just is as simple as it can possibly be. And now we need to decode the actual section. So the actual section, we need to find the data. And again, it's something we can grab from here as well. So if you look for the section, we can see that this is where things should be. Well, not quite, but close enough. So in this case, we don't go to, we have our pointer here, which is called, of course, we need to have the sections here. I think we have the sections, it doesn't really matter. And since this is not really pointed to the raw data, now it's actually the virtual address, which is actually where it is mapped in memory. So this value here is still an RVA, but this is how it is mapped in memory when it's loaded as a PE, as a binary, like so. And sections here and size of raw data is just fine. And we're doing the decryption here, and we're done. So that's basically it. Let's see if that works. So if I go ahead and use the code here and provide the address to myself, well, actually I need to grab that using a get module handle perhaps. So we need to maybe add another piece of information here. But let's see if we can grab this from the PEB perhaps, if it's not reserved here somewhere. So let's see, in process parameters maybe. No, we don't have that here, so I'm going to unfortunately call a get module handle. So let's go ahead and have a get module handle, another function here, and that's going to be decl type of a get module handle, and the A version doesn't really matter, and we're going to use the same ideas as before. In fact, I don't actually have to make it global, let's just use it as a local function, get module handle A. So we have that, and we now can call p get module handle with null. This will return the pointer to where we are. The executable is loaded into memory. So we just need to cast that to a DOS header to make it easier for the function that we're going to call. And that should be it. Let's see. So at this point, just to verify what is the state we're in, Darkside right now is having its code properly visible. So we want to make that invisible and then run our Darkside to see if it can decrypt the information correctly. So once we do that, now the Darkside code in text1 is invisible. So let's see if Darkside runs correctly. If it runs correctly, it means that it knows how to decrypt its code at runtime. And you notice that something is wrong. It took a few seconds, which means the process actually crashed. And the reason the process crashed is because we have some other things, one other thing that we missed here. Because we're looking at code here, so the text one here is code, code is not normally writable. In fact, if you go back here, we can see that this list of sections here, text one, just like the text section, is readable and executable, but not writable. Which means that when we try to write the information back, we got an access violation and the process crashed. And so the first thing we need to do before actually making the changes here, these changes are going to crash the process. Instead, what we need to do is first to map the memory into read-write and then do the work. So we need to have yet another function here. That's going to be a virtual protect. We need to change the protection of the memory. So virtual protect and virtual protect, not to make any spelling mistakes here. Let's grab it again and make it a global variable. So now that we have that, we can go ahead and make the required change when we're trying to decode the code. So we're going to call p virtual protect, We need the address, which is buffer. We need the size, which is size. The protection we want is read-write, and we're going to go back and get the old protect as the last argument, which is very convenient because we want to restore that. So we have here the old protect. So we're doing the work, and then just before returning, we're going to call virtual protect again, essentially copying pasting the same code, but changing this to old protect. I want to get the old protection, which is going to be read and execute, which is what we need for code. So once we have that, now we should be good to go. So the first call here is going to encrypt this section. And now if I run Darkside 2, it should work. So it still seems to be something wrong there. Something seems to be wrong because I didn't see that there was a little delay there. If I run this, you can see the image is still fine, which means something is still wrong in what we're doing here. So we had here the number of sections, we find the section, we're changing the protection to read-write, and then we're making the changes here, but something is apparently wrong. So let's see if we can figure this out by running this code. Again, these things happen. It takes sometimes several attempts to figure out what is going on. So let's just bring a breakpoint here and see where things get messed up. Okay, so we have 0 here in access violation because right. I have a spelling mistake here, which I exactly tried to avoid. So now it should be fine. So let's dispense with debugging and have faith. So here's first making Darkside bad, and then let's run it. Still something is wrong. Still doesn't work as expected. Again, so unfortunately we have to debug. Okay, so we got to this location. We have buffer here. We have size. Size is 0. That's not going to be good. Size is 0, which is definitely not what we want. So we have here something is definitely wrong here. Okay, so yes, I see the problem, and that's because we have equals to 0 here, which is really something we shouldn't have. We have our own equal strings function here. So now maybe this would actually work. Again, making Darkside encrypting it's a .text section and running it. This time it runs, I think, correctly. So here goes. You can see it's now not properly opened. Let's run it again to encrypt back. And now it's running again successfully. So here's what Darkside, this is how Darkside could have been built in a similar fashion. Of course, in real life, you would not encrypt a single file. You would have some kind of search pattern, such as find first file and find next file, things like that. And then you usually find files of a certain type, such as certain extensions that you want to encrypt and all that stuff. So that's not really the purpose of this demonstration, but we've seen how we can do these kind of interesting things by encrypting sections. We have just one import here, and that is basically it.